Hey class, in this lesson I want to take a look at this concept of fluid statics. And in physics, fluid statics refers to sort of looking at the behavior of fluids that are at rest. So we're ignoring the other forces that could be involved here. They're at rest, and so if they're at rest, we're typically looking at the concept of buoyancy and how the forces acting on the object are affecting whether or not it is positively, negatively, or neutrally buoyant. All right? So for this, to jump in, let's get ourselves an image here. We're going to need an image. So let me go ahead and I'm just going to draw a rectangular prism. All right, I'm just going to try to draw something that represents a nice rectangular prism. Simply because we're going to find out that this is an easy way to really kind of grasp this concept. So that's fairly three-dimensional. Although I guess if I did this instead, right? I'm just thinking about this. What happens if I did this instead? Come out this way and then come across. Yeah, let's do that. It's kind of, sort of, hang on. All right, you get the idea. That's kind of close. All right, kind of close. I know. There's going to be somebody who's going to say, all right, Tab, you should take a little more time. Yes, and I do see that right here, if I had to fix that spot, I could get it lined up more, but I don't want to waste too much time. So let's just jump into this. So rectangular prism, let's just say we know that there's our water line, right? And I'm going to go ahead and move this thing below the water line just a little bit so that I have some room to sort of exaggerate some of my illustration here. All right. Well, we know that there would be some fluid pushing down on top of this object. And we know that there would be some fluid pushing up on this side, plus pushing up on this side right here. Okay, let me center that a little bit more, right? And we know that we could just label this side A, we could label this side B, we could label this side C right here. And I'm going to label this, the top. We know that there is pressure coming down on the top right here, and I'm going to call this Y. Okay, simply because it's vertically straight up and down. All right, that's the only reason for that. And so we can distinguish between side C of the object and the vertical direction of water pressure. All right. Well, we know that this is the force up at the top. Okay, that we would call this down here force at the bottom. So I'm just writing force top, force bottom. All right, and all of this right here. So the distance from the water line to the bottom of the object is the entire distance, the displacement, the change in y from the top of the water line to the bottom of the water line. Okay, so now we've got this labeled. Now we can start doing some conceptual stuff with this. It doesn't matter what the numbers are. We're just doing some conceptual stuff. All right, so there's a couple things that let's think about this here. From the image, we know that we've got a buoyant force. And that buoyant force will be equal to the force at the bottom minus the force at the top. Okay, the force at the top pushing downward. If we were to go back and figure all this out, we would see that kind of makes some sense. All right. Now, to go further with this, we need to jump backwards in thought just a little bit. So we're dealing with a fluid. So we're dealing with pressure, and when we're dealing with pressure, it's important to understand some dynamics, because the pressure here can be pushing on one side, or two sides, three sides, and when we're talking about sides, we tend to talk about either area or we talk about volume. All right, so we're either talking about something along a square or a cube feature, characteristic of the object. So when we're talking about fluid pressure, okay, when we're talking about fluid pressure, there's a couple of things that you need to be familiar with. That's a capital P, all right? And so we would say the pressure equals the force divided by the area, or that pressure equals the density, and this is rho, the Greek letter rho, times acceleration due to gravity times y. And so this right here is our density. Okay. This right here we know is our acceleration due to gravity. And this part right here, we know that this would basically be the height of the fluid. All right. Basically pushing down on that, and we can see the y right there. Okay, so I've already identified that. All right, so that's another reason why I use the y, because it is a vertical, but also knowing this equation here, I just kind of set you up for this so it would make sense as we were discussing it. Okay. So now with that said, here's where we can take concepts and we can start doing some substitution. So off to the side for a second, if we take a look at this equation here, pressure is the force divided by the area, then we can rearrange this to say force is pressure times area. All right. Now don't confuse this with the unit that you see called a Pascal. Now Pascal is the unit that we get for pressure from this equation right here, all right, which is newtons per meter squared. All right, don't confuse this. This is where the letters are extremely important, whether or not you write them capitalized or lowercase. So area is a capital A. Okay, so just to draw your attention to that in case there might be some future confusion with something that I write or something that we're discussing in class. With that said, we can rewrite this now to say that the buoyant force would be, if force is the pressure times the area, then we would get the pressure at the bottom times the area minus, for now this one right here, we go the pressure at the top times its area. Okay, I don't know why I made that so curvy like that, times its area. All right, all we're doing is substituting and realizing that we're going to be able to expand this out and take a look at our concepts and bring in what we know about an object's buoyancy. Because remember, you've learned in chemistry or in some other past course that when objects are submerged in water, they displace X amount of water based on the volume of space that they take up. With that said, that brings us to this equation right here, because you understand the concept of density. All right, and density, remember, that's that part right there. All right, so with that said, we can come over here and now we can substitute for this P and this P. We can substitute all of this right here for it. All right, so now we have the buoyant force. All right, it is equal to the density times the acceleration due to gravity times the y, and then this would be the bottom. It's still the bottom because all we did was take this P and expand that out a lot more. That's all we've done. Times the area minus, and we're going to do the same thing with this P here. We're going to expand that out some more, okay, to include density into this, because density does factor into this, because this is where we're getting the volume of our object. All right, so that would be the rho times acceleration due to gravity times y at the top times the area. Okay. Now we see here a couple of things that are interesting. We see that we have right here and right here, we have gravity and density. And we see here that we have area. Those are similar variables in two different places. Since they are similar variables in two different places, then let's go ahead and factor them out. Let's just go ahead and factor that out. So we would get the buoyant force equals, all right? So we would get rho g and then a, and what we have left is the y at the bottom minus y at the top. Okay? We're going somewhere with this, I promise you. Now let's think about this a little bit further. We still have, it looks like, we still have our rho g a. Okay. So at the top, at the very top of this, what we see is the y plus the c. All of the pressure that is, I'm sorry, at the bottom. We had that right there. I literally looked at the top of this thing and started thinking on top. I looked at the top right here and my brain just went to the word top. All right, pardon me. So let's back this up. So right here, y at the bottom, we have this right here. So we already identified at the beginning that is whatever the y up there in yellow is plus the c. It is all of that, right? So let's go ahead and now substitute this right here, which is y plus c. So if we knew that measurement, now we just bring this down, and the y at the top, well, that's just this y right there. Okay? This is nothing to memorize. What I'm doing is showing you step by step how we can take what looks like not a lot of information, and if we bring in other concepts, we can basically get this factored out and thought about, right? So let me go ahead and I'm gonna just try to make this a little bit smaller for you. Let me go ahead and resize this, and I'll move this up. All right. So now let's think about this here. We have y minus y. So now y minus y goes away. So we've got the buoyant force equals rho g a, right? And now we've got basically times c. Now let's think about this for a second. We've got area and c. Now come off to the side here. When we measure area, we're measuring something squared. When we're measuring just side c, that is just one of the dimensions in the measurement. Well, we have a times c here, so that means we're going to wind up with something cubed as far as that goes. Okay? We're going to wind up with something cubed at this point here. Well, if we're winding up with something cubed, that's volume. So now we come back here. Our buoyant force is equal, we have the rho, g, and a times c we now know is a cubic function. So now we have a capital V for volume. Now let's think about this for a second. Hopefully you don't hear that dog barking in the background. If you do, I apologize. So now let's think about this for a second. We have, let me highlight this. Oops, that's not a highlighter. That was my eraser. We have rho and we have volume. if we think about this, we know that you sometimes have seen this. Let me go ahead and erase this part right here. I'm going to use this side for scratch paper for you. You've seen density equals mass divided by volume. Well, physics, they tend to sort of like to write it this way with that rho symbol. Okay? Well, if you think about it, mass equals the density times the volume, right? Well, you should notice that this right here is that right there, that P times V. So what are we going to do? You guessed it, we're going to substitute again. We're going to go mass times acceleration due to gravity. And you should recognize this equation as a fundamental equation that we use when we figure out force. So what we just did was we proved, we sort of mathematically supported the concept that when fluids are static, when they are at rest, that the buoyant force would, the amount of force that is on the top of the object versus the amount of force coming up below it would equate to what the buoyant force would be. And of course, if you have a greater force coming up from the bottom, then you would have something that would be moving towards more positively buoyant because you have a greater force pushing upward. If you have more fluid above, in other words, on the top, then at that point there's greater force pushing downward, and there would not be enough buoyant force to push it up. It would have a negative buoyancy. And then if in these equations, if it basically stays in one place in this fluid that is at rest, whatever it is, doesn't matter if it's the air, doesn't matter if it's a liquid, fluid is fluid, then it would be neutrally buoyant. Okay, so what we just showed was the weight of the displaced fluid, which is that right there. The weight of the displaced fluid is equal to the mass times the acceleration due to gravity. So at any point in time, we can use this equation, we can use this equation, we can use this concept. We can use any of this at any point in time to solve whatever we need to, depending on what is known about our object and where it is in the fluid that it's suspended in. If we know how much fluid is above and all that, and then we know its dimensions, we can somehow either extrapolate, we can either derive out, what its dimensions are from this concept here, or we directly have them. We can just plug everything in. We can solve all this, but it fundamentally comes down to mass times acceleration due to gravity. So again, all these equations are fundamentally all interrelated. It's just that we tend to parse them out one equation at a time so that we can think about a particular situation. But what you see from this video is when it comes to buoyancy with fluid statics, it's a lot more complex than just this thing is in water and it's either pushing up or pushing down. It can become much more detailed and complicated. And of course, you have some practice problems to work on this. But that's why I wanted to make this video, to help you out. So it was great learning with you. I hope this helped a little bit. Stay curious. I will see you in another episode real soon. Enjoy those practice problems. Take care. Bye-bye.